and this one. Okay.
Thank you. Alex, could you please share the screen?
Yeah. And also you
I can read this.
Yeah, you can share and
yes.
Go to your download as well.
Yes. Okay. Okay, so I'm going to share with you the address for downloading the notebooks. So let me just close this. That too, and that too, I think. So it is not that, it's 14GO CK RUN. Okay, so that's the link for the notebooks of this session. I have to download them myself. On downloads folder, yes. Now closed. Okay, downloads is the third one. Extract. Closed. Okay, yes, thank you. I'm going to do it right now. So Zoom, share the screen, share, and I can actually paste the link in the chat. Okay. It's not working? It is working? Okay, thanks. Okay, so is someone here who do not know what a differential equation is? No, okay, perfect. So yes, you have essentially 3 types of computation with differential equations. From the past, ancient times, let's say before Poincaré, you know, Newton, Leibniz, Bernoulli, all these people were trying to solve analytically differential equations. That means that you have a differential equation and you want to find all the functions that satisfy that particular equation. There was later a moment with Liouville, who shows that even very simple differential equations that have solutions, the solutions can be written explicitly as a combination of, let's say, elementary functions, exponentials, cosine, trigonometric functions, square roots, wherever. So it's a similar result to that one of Galois with polynomials. So if you have a polynomial, let's say something like a times x squared times x squared plus b times x plus c equals 0, where the unknown is x. Let me just do a quit to clean the memory. Okay, so if you have this equation, you can solve it. So this is not a differential equation, it's just an algebraic equation. You can solve it, you have a formula. Everybody's happy. But you may try to do the same, but with a higher order polynomial. So instead here of a x square cube square x plus d equals 0. So that's of order of 3. And actually you can get the solution in terms of the coefficient. Of course, it is a more complex solution, but you can get the analytic solution. But then if you continue doing that, actually try it with degree 4, you will get a bigger solution here. 4 solutions, of course. Okay, it's a formula. But what happens if I go to degree 5? Well, if you go to degree 5 or more, it is actually provable that it is not possible to write the solutions as a combination of the coefficients in terms of something that is called radicals. Radicals means in terms of elementary functions, square roots or nth roots of something, plus, minus. So that's a theorem from Galois, okay? That says that it is not possible to do it, to construct a formula for the general solution of a polynomial of degree higher than 5. That doesn't mean that the solutions do not exist. Actually, there's another theorem, D'Alembert-Gauss theorem, that says that there's always n solutions to a polynomial of degree n. So if you really want to find the solutions, or if you really want to understand something, you have to look for different approach to solve the equation. So the first approach is analytical. You try to find the explicit solution of an equation, algebraic or differential. The second approach, which was almost at the same time that the approach of analyticity, was invented by Euler. So Euler was a Swiss mathematician, and he invented the Euler method, which was giving a numerical solution to differential equations by a very, very simple remark, which was, okay, if I have a function, this function is smooth enough, I can approach at a point the value of the function by the value of the tangent at that point. So if this is the point Tn, I can approximate the value of the function a little bit later in time, plus h is small, by the tangent. So the real value is here, the approximate value is here. This is true, this is approximate. And he invented numerical methods in this way. The problem, it was too early at that time, because even if these type of methods are easy to understand and easy to compute, in the 17th century, computers haven't been invented yet, so they were theoretical methods. It's funny because today we understand that as a applied method, but in that time it was a theoretical method that can solve approximatively well the differential equation. Okay, so if you have y prime of x equals some function of x, y of x, you can solve this approximatively from the initial condition, saying that the value at the time, next time, is the value before, okay, this is the value before, plus a little amount of error times the function f at xn, yn, okay? So when Euler invented that method, it was a theoretical method, not useful, and we have to wait for the invention of computers. And if you saw the movie, what was the name of the movie? Shadows, you know, at the NASA? The ladies, yes. What was the name of the
I don't the story myself.
Ah, okay, thank you. So yeah, in that movie, they have an idea to use that type of things, and it's yes, we are too young, so we do not need that time, but computers actually appear very recently. Okay, well, whatever. So this is the second method you can use, numerical method. The third method is to use something that is called the qualitative theory of differential equations. So the qualitative theory says, okay, Liouville told us that we cannot solve the differential equation. Let's do not solve it. Euler has a method, but it is not useful in practice. Let's do geometry to understand the dynamical system associated to this type of things. And you will see that we can do that also here. Just to give you an example, let's say you have the differential equation y prime equals y of x squared. Even if you don't know anything about how to solve this, you can say something which is qualitative. What can be said from here? This is a square, so this must be positive. So the function I am looking for has a derivative which is positive. That means that the function y is an increasing function, okay? So for very cheap, you have an information, a qualitative information is that the function is always increasing, just looking the differential equation, okay? Okay, so that's the introduction. Let's start with ordinary differential equations. And later we are going to move into PDEs, partial differential equations. Probably just one word to say is that the theory of ordinary differential equations is quite complete, it's quite homogeneous. Of course, there are a lot of questions that we do not know the answer, but it is more or less complete, let's say. The PDE theory is another word. Essentially, each partial differential equation has its own behavior, its own physics, biology, or whatever. So the theory and the tools associated to each PDE might vary strongly, okay? Okay, how do you solve ordinary differential equations in Mathematica? Ah, yeah, thank you. I forgot that. Back, close. Yes. Quit. Okay. Okay. Is it good? Yeah. Okay, so file open. 3 OD. Good. Okay. So the first thing is symbolic solutions. So our first part in the history. The command is DSolve. And you can use it in the following way. You say, I want to solve this differential equation. Please do not forget the double equal sign. That's very important. Then you indicate which is the unknown function you are looking for. So here I am looking for y of x. And then the independent variable is x. And that's all. Differential equation, unknown function, the independent variable. Okay. Here I give a nonlinear differential equation, and I am looking for a full simplification of the first solution of the solution. Okay. So this notation that you look here, it is known as the Polish notation for a function. And it is equivalent to the other one you already saw. If you have a function, you can evaluate it at a point, f of x. You can do it with arroba, or you can do it with the Polish notation, which is like this. Okay. And that's all. Okay. This is the same. And this, yeah, this is the Polish one. This is the prefix. And this is the traditional. So they do the same. So what I have here is simplify the solution seen as a column of this thing. Okay? Well, if you evaluate that, you will get the solution of the differential equation, which is this function. And you can see something interesting is that there are some constants, C1, C2, that are integration constants. This is a second order equation, so I have two integration constants. The common result, as many functions in Wolfram language, is a super function. That means that the function itself can call different sub-algorithms, subroutines to perform some calculations. So when DSolve sees a differential equation, it will classify the differential equation into different properties, according to different properties. Is it linear? Is it not linear? Has its own Galois or Lie symmetries? And then follows up the solution. Okay. Well, that's all. Now we can do the same, but for partial differential equations. Yes. Okay. Okay. Sure. Let's give a simple example on that. If you have the command solve, x plus 3 equals 0, and you are looking for x, okay? This equation has only one solution, which is -3. And you see that you get a list of x arrow a value. Okay? Why you have a list of lists? Well, if you have more than one solution, for example, if you have x squared minus plus 3 equals 0, you have two solutions. Okay. So since you have two solutions, each independent solution will be put inside a list, a sublist. Okay. Now, the arrow means a replacement rule. For example, if I say here x arrow this, that means that x is not being affected to the value. It says just that it should be replaced by that value in order to solve the solution, the equation. Okay? What is the advantage of that? The advantage of that is that you do not affect the variable x to a particular value. Okay? You get x free of evaluation. So x remains an abstract symbol. So that's the same here, but a more complicated example. Instead of having y of x equals to that expression, you have directly a replacement rules. You will see that it is useful for more things. Yes? Yes. Yes. Now, there's another way of getting solutions. Instead of writing solve, I can say solve values. If I say solve values, I don't get list of replacement rules, I get directly the values of the solution. So depending on what do you want to do, well, you might prefer one or the other, okay? For DSolve, it is the same. If you say DSolve value, you will get directly this solution instead of the replacement rule. Now, you can solve partial differential equations. The Burger's equation is a nonlinear dispersive equation. If you know this term, it can be seen as a one-dimensional version of the Navier-Stokes equations. Okay, so this is 1D. You have here the speed that depends on the solution itself, so it is nonlinear, and here you have some diffusion coefficient. And you can see that there are some parameters, nu, that's the only one, which is an algebraic parameter. It has not a specific value. And when I launch the computation, I get this solution that involves a special function known as the error function. So the error function is the antiderivative of the Gaussian. And this is very common in solving differential equations with Mathematica. Some functions are defined by itself as solutions to differential equations. And in mathematical physics, you have, I don't know, like Bessel functions that are defined as solution of differential equations. So you might see this type of functions in the output. Okay? Well, not everyone. Not everyone. Okay. You can solve also systems of differential equations. Here is a matrix, this, given by a row. So it's 4 minus 6, 1 minus 1. And here I have a linear system. X prime equals a times x. And the solution of this type of systems can be given by the exponential function of the matrix. Okay. So, yes, yes. A dot x can be written in the long form as dot of ax. Okay. Yeah, and so if you have a differential equation y prime of x equals a matrix A times a vector y of x, the solution is y of x sub exponential of the matrix A times t times the initial condition vector y. Okay? So here, when we solve this system, you know, those exponentials here come from the exponential of the matrix A. Okay? Now, a more tricky type of differential equation is known as differential algebraic equations. It is the case when you mix some differential equations and some constraint, usually they are seen as constraints, of algebraic equations. So for example, this equation is a system. I have an unknown which is x, y, z. They must satisfy this with differential equation, but this is not a differential equation. It's an algebraic equation. They are not derivatives. And this is also an algebraic equation. They are not derivatives. And we can solve that type of things too. Okay? It is more difficult to solve because you have to satisfy the algebraic constraints every single time. There is another type of differential equations that we can solve in Mathematica. I am not talking about that today, but you can solve delay differential equations where you have some term depending on a past time. And you can also solve a much more trickier type of equation, which is integral differential equations, where you mix derivative parts and integral parts. And that type of equation are difficult because they are non-local usually. Okay. For example, if you say, I don't know, well, this is a PDE version, but it is the same. This is the heat equation. Okay, so that's easy. The heat is just Fourier law. But if you say, okay, the solution must be satisfy something like this. Well, this is an integral term, and you are mixing derivatives and integrals. So this is local. The derivatives is just the tangent, but this is non-local. This is seeing everything in space. Okay, so this is much more difficult to solve. Okay, many other forms can be solved as well. An explicit listing of the types of equation that can be handled is in this tutorial. Okay, so if you want much more deeper information that we can cover today, you can go here, especially look at this chapter, nonlinear ordinary differential equations with these symmetries. Yeah, so that usually these symmetries are considered as the highest level of method here. They use symmetries and that kind of things. Okay. Now, we say, okay, I want an analytic solution. I almost never can have it. I may want a numeric solution, okay, but if I want to know what's the behavior of the solution at infinity, it's not working because I am not going to solve the infinite number of terms. So it doesn't work. Maybe I want an analytic estimate. So you can use asymptotic DSolve value. So asymptotic DSolve value, we use asymptotic methods. So in physics, maybe you are familiar with the WKB perturbation method, this type of things. It's an asymptotic method. So here you have this differential equation, and you say, I want an asymptotic solution at infinity of order 2. Okay? So you say this, and you get that in general simple expression, depending on the scale of order x. And you get this solution. Okay? Any question? Okay. Yes? Well, the assumptions that always Mathematica do with any symbol is it is complex unless you specify something different. So that's the first thing. The other thing here, it may suppose enough differentiability to perform some computations. If you have, I don't know, the derivative of an integral is the integral of the derivative. These type of things are given as a fact, okay? So yes, it can suppose many things to solve the differential system. If you want to control the, for example, you have, I don't know, if you have here a parameter, maybe, let me think of a simple example. Yes, let's say something like a times x equals b. In this example, b must be different from 0 to have a sense, because if a is 0, you can't do that, okay? So here there's an implicit assumption that is a is not 0. There is another function which is similar to solve in its syntax, which is reduce. The difference between solve and reduce is that reduce we construct an equivalent, a logical equivalent expression of the problem you are submitting it. So for example, here it says that, okay, you asked me about AX equals B. This can be solved if A is 0 or B is 0. In that case, you have infinite solution. Or A not 0, and then X is B over A. Okay? So you can control these type of things too. And the other thing is assumption. Assumptions, the assumption variable. You can add inside, for example, let's say I can say, assume that A is strictly positive, okay? So if it's assumed to be strictly positive, let's say I want to simplify the square root of A power 2. No, it's, yes, it's the square of, the inverse is the square of A and then the square root of that. This is not simplified by default because A is a complex number. So I can just take out the square. But if I add the assumption that A is a positive number, now I can evaluate again this and get A, okay? So look at this in the documentation if you look for a specific type of use.
If you say A is greater than 0, does it work the same way?
Yes.
And then not the signified.
Yes. The difference is that here this is a global variable, so it will be assumed everywhere.
It's not for the whole node.
Yes. Okay. And the other for a specific computation. So asymptotic, we have different asymptotic things. Asymptotic integrate, if you want to compute an integral in an asymptotic expansion, asymptotic sum, asymptotic R-solve value. Okay, that was for the analytic part first. We will talk again later. Now, numeric solutions. Yes? I don't. I know that yes, in just one simple case, which is if you specify the limit. For example, if you are looking for, I don't know, Schrodinger, the Schrodinger solutions, the wave functions. We're looking for wave functions. Typically, you say that wave functions must be normalized in L2. So that implies that the limit when x tends to infinity of psi of x must be 0. So you can specify this type of things. So it's an asymptotic boundary condition. But I don't know if you can specify that the growth at infinity might be some algebraic growth or something. I don't know. I don't know. But yes, that yes. Okay. Okay, numeric solutions. This part is very fun, especially with PDEs, because you can construct domains using the geometry functions that we have. For example, here, rectangle is a 2D region. So you can construct things like this. Of course, you can construct more complicated things like this. Using manipulate, you can do this. Yeah, you can construct polygons with every shape. You can literally do whatever you want with polygons. The idea here in PDEs is that you find a domain where you want to solve the differential equation. You can do unions, intersections, difference of regions. In 3D, you can also do that, cuboids, or maybe more complicated elements, okay? And you can, well, we will see that later. This notebook is a little bit old. It's probably from version 11. So now we're in version 13. There's a huge step in version 12. In version 12. That is solving PDEs with nonlinear finite elements. So before that time, we were only allowed to solve essentially this type of differential equations. So this is no longer true. Now we can solve much more general things. But you know, this is a general form. You have coefficients. This is a vectorial equation, so it's not the scalar case. But essentially, you can, by the past, just solve that with finite elements. Now we have nonlinear finite elements. So the problems you can tackle are more interesting. If you go here, you say Wolfram new in 12. You can select any number between 1 and 13 if you want to see what were the new adds to that version. So version 12, the last one, introduced nonlinear finite elements. And here you have some examples of what can be solved using nonlinear finite elements. For example, here you have the transient Navier-Stokes equation. How do I increase the, like this? So you have here the code, you can just click and copy on your notebook. And at the end, you get this video, okay? Here you have the Wolfram language code to construct this. Okay, so this is nonlinear, obviously. And now we can solve that type of things too. There are other examples that are quite nice too. For example, the Gray-Scott model in biology. So this is a system of PDEs, nonlinear PDEs. And the solution is a pattern like this, okay? So biologists are interested in that for morphogenesis. Okay? I'm going to come back to the notebook. So here you have some, check your understanding. Select valid Wolfram language syntax for solving the differential equation Symbolic. Okay. Which one is good? Maybe a random person, I don't know. Want to be a random person? You? Okay, it's all of the above. Maybe, actually, I tend to say that it's just the first and the second. This might be not good. Let's see. It's right and it works? Okay, well, it's all the above, maybe. I don't know what do you get if you do this one. It's not copying it correctly. DSolve of y prime of t equals t squared for t from 0 to 2. No, it's not. Yeah, thank you. You're right. Okay. No, wait, I don't understand it. What is this? Because, well, the difference, we are going to study now the difference between those three. What's the difference between the first and the second one? Is the square bracket here with T. Okay. So this one and this one will have a difference in the output. The first one will return an expression on y of t, and the second one will return a function. So one is an expression, the other one is a function. So let's see that right now. Blah, 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 y of t, comma t. Okay, so the first one returns a list of replacement rules where y of t must be replaced by that in order to get a solution. Okay, now let's change this a little bit with y instead of y of t. And then you see that y must be replaced not by an expression, but by a function. It is the function that the variable t, it associates t of t cubed over 3 plus c1. Okay, we will see what's the difference now. Now, there's another thing I want to show you, which is DSolve value. So I take the same code, but instead of using DSolve, I use DSolve value. And the same code here, but instead of using DSolve, I use DSolve value. Okay, so I have 4 different values with this one. And I don't know exactly what those different ones check. The 4 first, the first 4, they obviously return the same solution, but not in the same form. This form is maybe the most basic one. It's just a formula. It's just a formula. Here is a function. What is the difference between this and this? This can be evaluated in something. This can't. For example, here you can say this on A, and it will return A cubed over 3 plus C1. This version can be evaluated on something. This can't. It's just a formula. Now, the third or the second one there is a replacement rule. So you don't get directly the function, you get a replacement rule that can be used to do something. And there you have y of t, which is more or less the equivalent of this one, but with replacement rules. Okay, that's maybe incomprehensible, but in practice, what changes? In practice, it changed the next step. If I want to plot the function, if I want to plot the solution, what I'm going to do, well, this is C1. So if I want to take out the constant, I'm going to add an initial condition, okay? Y in 0 is 1. Okay, and copy this here, here. Sorry? Oh, yes, you're completely right. Comma here. Tac, tac. Thank you. Here, comma. Tac, 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 tac. We will see that later. Okay, so now if I want to plot the solution, what do you want to use? Probably the best one is this one, the last one. Okay, because if I want to plot, let's call this solution 1, solution 2, solution 1, solution 2, solution 3, and solution 4. So if I want to plot the function, what I can do is plot solve for t from 0 to 1. This works. Okay. The third one will not work directly with this. Why? Well, because it's a function that has been evaluated somewhere.
So if I want to use solve 3, it's not working. If I want this to work with solution 3, I have to add here that that function is evaluated on t. Okay? So that's the first thing. So 4, I can use it directly like this. Here I need to add square brackets of t. Now, with the second one, obviously this is not going to work directly. What do I need to do in order to use solution 2? Well, I have to get y unevaluated to t. So I have to do y of t and recover that value from solution 2. Okay? So it is not just adding square of t, it's adding square of t and replace y of t by this. Replace y by this. Okay. And now if I use the first one, obviously I have to replace by y, and this will be replaced by a function, and then I have to evaluate it. Sorry, here I have to replace y of t in one single step. Okay, so this will work in a different way, but return the same result. Okay, so that's one first difference of use. The output will condition the way you have to use it to plots, but also, and that's also an interesting thing, is to verify the differential equation. For example, you get the solution, you're happy, but do you want to verify if is it really a solution? If you want to verify if it's a solution, what do you want to do is to replace the expression you find in the differential equation. Okay, but that will come with some problems. Yes?
If I put solution of t as a function.
Yes.
With the DSolve value. After I cannot plot this function.
The 1, 2, or 3, or 4? Okay. Why you can't plot it? Your code. It's the same example. I can see it. Okay. Yes. And then it's the word. This is that.
One thing I like about the ratio group is that instead of floating y, float sine y or sine of 1/2 y squared plus y squared. So you can evaluate the expression of expressions that are linear.
Yes, that's the power. That's the power of. Yes, exactly. That was actually my example just now. Okay, so it's better to answer that first. Yeah, no, I know. It's in order to make it clear. Let's do that first, and then we come back to that. If you have a formula, which is the equation here, the equation is y prime of t equals t squared. Okay? This is my differential equation. And now I want to know if the solution I get satisfies this differential equation. Well, what I can do is to replace y of t by the value I found before. So I can say replace y of t by solution 1, for example. Okay?
So if I replace y of t by the replacement contained here, 1, I get this list. So it might be similar here. I can just say replace that solution in the differential equation and see if it's 0. But it will work for the second one, but not for the first one. Why it will not work for the first one? Well, because here I don't have y of t. I have y prime of t. So if I try to replace here with solution 1, okay, blah, 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 solution 1, it hasn't been replaced. The reason is that this is not y of t, but y prime of t. So if you want to verify the differential equation, you have to use the second one,
okay, which is the function expression of y. So if instead of doing this, I use sol2, I get true. So it is a solution. Okay. It might be a little bit complicated to understand, but the only thing you might understand here is depending on the command and on the use of the syntax, I get a different form of the same solution. And depending on what I am interested in doing, I might choose one or the other. Okay, that's basically the idea. This can be used in this way, or in a more complicated example, as Constantino said, is, for example, replacing by derivatives or something. NDSolve. Well, this is numeric, so maybe later. I will show you later. Now, the question you asked me is a very important question. The question here is, okay, I already have my differential, my solution to the differential equation. Now I want to give it a name. I want to name it, for example, here I say solution 1, 2, 3, or H, F, any name. And then I want to use that to do something. Well, obviously, the best one you can choose is this one, because you get directly a function. So when I say solve 3 of this, I can evaluate solve 3 in anything. For example, solve 3 in A. Well, A was the matrix, so in M. Okay. This is the type of things you want. So it's better to choose the third type. They are all transformable into each other, but you have to pay some amount of transformation. Okay, so for example, if I want to use the second one to define a function, I have to do something similar to here. Replace, evaluate, but the best you can do is to use the third one. Okay. Any questions about that? No.
Why solution of M underscore doesn't work?
Yes, so what you were doing something like this, f of x equals, you took which one, the first? Here? Well, it's not important, it can be x or t or wherever. Yes, but it depends on which one you want to use. If you want to use the third one, you can just say solve 3 of t. and then just say plot f of t for t between 0 and 1. Okay. That's the best you can do. You can do it with the others, but it's a mess. Okay? So it's possible to do it. Okay. Okay, perfect. Well, page number 4. Now we are going to do numerics. Okay. And so the syntax is almost the same. You have the equation, you have the conditions, so the initial conditions, or if it's a PDE, the boundary conditions, then the unknown function, or a list of unknown functions if you have a system of differential equations. And then the range where the differential equation has to be solved. Okay, so that's the new thing with respect to analytic solutions. You have this third range for the independent variable. And what you get is interpolation function. If I solve this, you see here that my result is not a formula, it's an interpolation function. Okay, this interpolation function can be plotted directly, as we just do before. And all that we say before is applies to the NDSolve function. So this is the same example as Constantino was talking about. If you have the solution solved, you can use it now from the numeric interpolation to evaluate other type of quantities, like the derivative. Here, this is the derivative of x, and this is the antiderivative of x, and plot it. Okay. So this is important. For example, I don't know if you have the Newton's second law, okay, you get the solution that will be a position, right? So if you say mass times the second derivative of x equals some force, the solution of this is a function f of x of t. But maybe you want to compute the energy, which is a function of x, and the derivative of x, which is the speed. So this is, for example, I don't know, 1/2 of mx prime squared plus some potential energy, let's say kx squared. Okay, this expression, which is the energy, is involving two, well, the solution and the derivative of the solution. So if you want to plot this, you can do it in this way. Yes? We have to use the evaluate when you are putting essentially a t or a x here. Here I put the x. So I get an interpolating function of x. Now, if I use it in this way, I get directly an interpolating function without x. So this is a function that I have to evaluate, and I don't need the evaluate in this case. Okay? So the evaluate function tells Mathematica to perform that computation before evaluating the rest. Let's do one example, one full example of analytic and numeric coming from physics, because I just remember this. So I try to show you a typical example from scratch, and that is complete. We're going to do that, okay? So, as usual in physics, I will assume M is 1 later. Okay? For the moment, we can keep it. So Newton's second law is that differential equation, mass times acceleration, x prime prime of t, maybe do that a little bit higher, bigger, will be the force that depends normally on T, on X. It can depend on the speed actually. So X prime of T. Okay. So this is my differential equation. Okay. Now I have to choose a particular force term. If we consider maybe a mass attached to a spring, and this is the basic length, and I'm going to measure x of t to be the length of the mass from its position at rest. Yeah, equilibrium. Thank you. So here the mass has, let's say, just one force, which is this Fr, which is minus k x of t. Okay, and maybe if this is inside a damping medium like oil or something, I have another force which is dissipative force in terms of minus gamma x prime. Okay, something like that. So I will use f to define a function that depends on x and the velocity v. And this will be the sum of those two forces, okay? So I have minus k times x of t minus gamma of x prime of t. So I define my force. Now you can see that if I evaluate again Newton's second law, this force term has been evaluated with the equation. Okay? Okay. Now I can ask Mathematica to solve directly this differential equation using DSolve. Please solve the Newton's second law with unknown function x of t, and the independent variable is t. Yes, here here is v. Yes, here is v. Thank you. Also, yes, thank you very much. Let's do a clear f like this. Now this is correct. This is correct too, and this is correct. Okay. You see that this analytic solution has the integration constant C1, C2, and it depends explicitly on the parameters. Okay. Okay, if I want to add some initial conditions, I say x at 0 is maybe, I don't know, 1. X prime at 0 might be, for example, 0 if it has no initial speed. So those are my, here is a double equal sign, so be careful. Initial condition. If I want to take into account the initial condition in my solution, I add it into the equation. So I say DSolve, Newton's second law, and I'm going to join the two lists. So join Newton's second law with initial conditions. The unknown function is f of x of t, and the independent variable is c. Okay? So now this solution takes into account
those initial conditions to determine the integration constant C1 and C2. Okay, and I get this expression. I think this can be simplified
a little bit more. I'm going to use DSolve value. And now I'm going to full simplify this. And I get the
simplified version of the solution. Okay. So that was analytic.
If I want to do some numerical experiment now, I can use the parametric NDSolve or just the NDSolve. But since we already talked about parametric NDSolve this morning, let's just use it again because it's the best. For me, it's the best. So I say parametric NDSolve value of the same thing here. Well, the same thing, yeah. I'm not going to change the initial conditions, so I can leave it in that form. Yes, this I'm going to leave it in that form. Here you have to put the model directly, huh? Because you want to specify the parameters m, k, and gamma. So here the unknown function is x of t. T is the independent variable, and the parameters are m, k, and gamma.
Sorry? I think no. I think no, but well, there are possibilities. Maybe yes, and in that case, it's okay. Let me know. And if it's not the case, actually, I have to define Newton as a function of parameters if I want to make it work directly instead of writing the system.
We can do that if you want. We can do that. So I take this and I'm going to say equations of the parameters m, k, and gamma, and I define a function here. And it will be here. So the interest is that now this has some sense. Okay, it returns an equation depending on the variables. So here I say equations on m, k, and gamma. Like that. This will be my solution. And again, I get a parametric function. Now I can say that I want the solution. Actually, here is, I have to indicate the interval of time because it's a numeric solution. So I'm going to indicate it like this. So clear solution. Okay. Solution is this. And now if I want to specify a solution, I say m, k, t, and gamma. Okay. Let's try to do it here. T might be 10. M equals 1, k equals 1, gamma equals 0, and 10 equals 10. So for that particular values of m, k, gamma, and t, I get this interpolating function. That depends on t. I'm going to take out this t by specifying here just x. And let's see what is the effect of specifying t or not.
So this is the parametric model. Now, if I evaluate the parametric model in these particular values, I get this
interpolation. So let's do it like this. Now I get the interpolation model function without t.
In the way, the first one. Just before when I have the t here. Yes. It's the same. The values of gamma and t will be the same form. The only difference is that here I have t. Okay. But this is the best. In my personal choice, having the function is always the best, because you can evaluate the function directly, derivate the function.
So I can do the plot. Well, let's say that is x solution is this function. And now I can say plot x sol of t for t from 0 to 10. Yeah, thank you. So my spring, when there is no the friction term, it is always oscillating as a cosine function. Now I can take this same graph and plot not only x, but always also the derivative of x sol of prime of t inside a list. Okay, so here I have the position and the speed of my mass. And if you plot the same thing, but instead of plotting both on the same axis, you use it one as x and the other as y, that means that you use a parametric plot. Then you get a circle in the phase space. So this is known as the phase space. Here is the position, and here is the speed. And how do you interpret this physically? Well, at initial time, my particle is here, starting from 1. The speed is 0. So the y of this point is 0. Now the ball starts moving there, so the speed increases, and the distance to the equilibrium position goes to 0. So at this moment, the ball is at its equilibrium position with maximal speed. Then the spring compresses a little bit more, so the mass goes up to -1 with a speed which is 0, and then come back, increasing the speed of the opposite side because it's going to the other side. It goes here, so maximal speed, and starting to decrease the speed. Okay, so it's doing this, the mass. And actually, we are going to plot that behavior using graphics. I'm going. The first one. Okay, so if I solve this, I get x, and here I have x and x prime, which is the speed. And what I saw is that I have, my solution is doing, is following a path, which is a circle in the phase space. That you will see will be related to conservation of energy. If I plot the speed and the velocity over time, it means that if I parameterize here with time, I have my solution, which is making an helix. Okay. How do you say that in French? Helix. It's a great word. like almost every word. But you have this. And if you project this helix in the x-plane, here you are going to have, well, this is not working. It's maybe too black. You are going to have the cosine function. If you project the, let's do it in Mathematica. So now, if I take this and I parameterize it with respect to t, I add t here, and I have parametric plot 3D, and I get my helix, okay? So if this function I project on the xt plane, I get my initial solution, which was the cosine, this one. And if I project that helix on the vt plane, I get the speed, so the yellow one. Okay, now we are going to continue that, but more graphically. That means that I'm going to do a manipulate of graphics. I'm going to draw a blue disk at 0, 0 and a radius of 0.25 and maybe 0.1. It's 25 is too much. And the coordinates of the center actually are not 0, 0, but x sol of t. And I'm moving that from t equals 0 to 10. And I'm going to say that the plot range is 2. Let's say it's 2. And add some axes. Okay, so this is my my mass, and the mass is moving go on down with the differential equation. Okay. So the theorem of conservation of energy says that this function is actually a constant of the movement. So if I take the function x sol of t prime square prime, the prime is here, and here is a square, plus k was 1, so x sol of t square. This is a constant function. So I say plot this. So plot the solution, plot the derivative, prime of t, plot the energy, and that's all for t from 0 to 10. So here you have the position, here you have the speed, and if you compute this quantity, speed squared plus x squared, you see that you get a green line which is constant. Okay, so that's the theorem of the conservation of energy. Now, this thing is actually a surface because it depends on two variables. So I can define an energy function, energy, that depends on x and v, and which is x squared plus v squared. And this is a surface, so I can plot 3D the energy of x and y. For x and y, 2 points of the disk of center 0 and radius 1. And what do you get is this energy surface. This is an energy surface where the particle is actually moving. Okay. And my solution will be a level curve of that function. So let's put this in a more colorful way. Color function, I like the temperature map. Mesh functions, the third one. Okay. So those circles you see here are the levels of energy that are constant. So you say level 0.5 of energy is a plane. You cut your surface by a plane, and you get a circle here. Okay, you get circles. Well, do you remember this circle? Well, it is one of those. When my particle has some energy, some initial energy, since the energy is conserved, the level of energy will remain the same all the time, and my particle is actually moving over one of those level curves. I can plot it if you want. I'm going to say show this with my parametric plot 3D, which is this one. Plot that here. So the show command allows you to superpose different plots. So here this will be like this, square. No, it's not square, it's just that. And here is energy of those two. And I'm going to say that I want to see that plot style, thickness 0.2 and red. Okay, so maybe go further here, 0.0 and 2 maybe. Okay, so what do you see here? The red curve is the trajectory of my particle in the phase space at a certain energy level. Okay? And the energy is conserved. Okay? The energy is conserved. What else can be said here? The energy is conserved because my gamma term was 0. Gamma is the friction coefficient. So if gamma is not 0, there will be a loss of energy. Then the energy will be dissipated. And since the energy will be dissipated, this will not be longer true. The shape will be different. Let's try to find what the shape will be. So I take everything from here. So here we are going to say when energy is conserved, I'm going to copy this section, paste it. So yeah, that's a very useful thing if you don't know it already. When you define a section like this one, you can actually just double click on the right to collapse everything in the contents, okay? And it's just collapsed there. If you want to open it again, you just click here, okay? So that was when energy is conserved. I'm going to do now when energy is not conserved. And I have to introduce a small gamma coefficient, maybe 0.5. Now the energy is dissipated, so the amplitude of the oscillation is smaller and smaller. So the mass do this. Okay. Now, if I plot the position and the velocity, we see the thing. And what will happen with the circle? Well, it becomes a spiral. Okay. And when the time goes to infinity, in the phase plane, the point is going to zero. Okay. When the energy is dissipated, when time goes to infinity, it tends to the equilibrium of the system. Again, the helix is not longer a helix, but more a spaghetti with this. The energy is not conserved. The energy is decreasing. So remember, the green one was the energy. Before it was a straight line. Now the energy is decreasing. And this, well, it's the way I told you. So it's the amplitude is less and less and less. Okay. The energy is the same, and my surface of energy will be dissipated. So you can see that instead of remaining at the same level, the particle is having a slower energy level. Okay. Well, that's a practical case. Okay. And again, there's a lot of information to share with you, but I prefer to take the time, maybe explain things more. In any case, you have the notebook, so if you have some problems, please just contact us. Here is a maybe more clearly explained way of what's the difference between both. It's the same thing I already told you about the dependent variable y of t, etc. So this has already been done. The only thing that changed really between NDSolve value and NDSolve is that part when the equation has multiple solutions. When the equation has multiple solutions, NDSolve value will return only one solution, and NDSolve value will return all the solutions. So here, since I have squares, I have some symmetry. NDSolve return 4 solutions, but NDSolve value returns only 1. And of course, I get an error message to tell me that therefore, if I have more solutions, I am just in 1. Why this happens? Well, actually, I don't know. It's a good question. I don't know why there's a choice.
In the documentation, if you want analyze the algorithm,
Actually, we can know the answer to this question, but I have to ask the developers. I tend to say that there's a good reason for that, but I don't know why. Yes.
Okay. Yeah, that's a very good question. It's notebook 2, I think. Let's go to that part quickly, okay? That's the boundary condition. This is one first step in answering your question. All numerical methods must discretize independent variable with a certain step size. A large step size results in faster calculation, but can decrease the accuracy of the result. It's the same price principle, universal price principle. If you want speed, you lose precision. If you want precision, it's like a taxing principle. Okay, so adaptive step size in NDSolve, you have one option, which is, well, the answer here is a little bit too complicated. Let me give you one first answer, which is simpler. If you say NDSolve something, you have an option which is max step size. Okay, so this is one simple answer. If you want to specify what's the maximum value that the step can take, you can use this option. There are a lot of options to control that, those parameters. This is a little bit more complicated answer. Here you have a package which is differential equations, and there you have this context, which is NDSolve utilities. So it contains all functions to analyze, to specify. Here I can see using step data plots what is the size of the step that my algorithm is using to solve this differential equation. So for example, here, clear t and x. Well, it doesn't matter. The only thing that matters here is the plot. So this is the solution. And if you want to see what's the step size at every x, use this function. And here you can see something interesting. The step size close to the origin is small. 10 to the power minus 5. But so that's a very small step size. But when I'm far from the origin, you see that the function varies not so fast. It is more, it varies less quickly. So I can take more and bigger step size because so essentially the function we are trying to approximate has oscillation or high oscillations in some region. The step size must be adapted locally. When you use NDSolve value, the function takes care about these kind of things automatically. Of course, you can force NDSolve to use a specific method, I don't know, method, so order 3 with static parameter. You can specify that. What is interesting here, and that's maybe something you may not know, is that NDSolve value, which is a numeric function, can actually use DSolve, which is an analytic function, in a subroutine to approximate more accurately the solution. So it solves some parts or use integrate or the analytic functions to get a better result in the numeric way. Okay. So that's the first answer. Now, the next thing here are all the options that the NDSolve function has. Let's print the options. Essentially, you have those, and those options have sub-options and sub-sub-options. I don't know if someone knows all the sub-options that exist, but I don't do it. So you can specify the method. That's the first thing you can say. Untitled or maybe at least a bit like this in the documentation. You can specify the maximum number of steps to take, the maximum size of each step, starting step size, the accuracy goal, precision goal, working precision. This might be interesting too, interpolation order. It's order 0 is by constant, order 1 is by straight lines, etc. And here is an example, okay? I have my equation, my solution, and you can see without any comment the step size is if it's small, then it becomes bigger. Now, I want to say to Mathematica to use a maximum step size of some value. So here, max step size, 10 minus 2. Now you can see that the plot actually respects that.
This is the state data of this solution. You can see that it is not going bigger than this compared to that. Yes, all the parameters are related. For example, the most simple case will be max step size. Actually, I think it's the next slide. No, it's not the next one. But for example, max step size is the same as, well, I think it's not listed here, but you can, it is equivalent to specify the maximum step size and something else, which is the inverse. What's called I think it's maybe in the second notebook here. So happily, we already end the first notebook, so we can go to the second one. Ah, yeah, again, I forgot to open it from Mathematica. Huh? Ah, okay. Thank you. Okay, so let's open from here. But well, the idea is you have some names, some options that are the inverse of the other, okay? So for example, if one option is say X, the other option has value 1 over X or something like that. So they are related, okay? Yeah, I know now the example. So let's say you have an interval like this. You can specify two different things. You can specify the step here, or you can specify the number of points. And those two options are related by dx is the length of the interval from 0 to L divided by n plus 1. Okay, so if you specify delta x, it is the same that if you specify the number of points inside the interval. Okay, so this is the inverse of this one. Okay. Number 2. This part is very funny. Events. I really like events because it brings some funny behaviors. Well, this is something on methods. If you want to specify Runge-Kutta, and for example, for explicit Runge-Kutta, you have sub-options. The sub-options are the coefficients, difference order, the embedded difference order. Well, you have a lot of sub-options, okay? Stiffness. This is an interesting property of some differential equations. Stiffness means that the scale of variation of the solution can differ from the interval you're looking for the solution. Essentially, you can think about a function that varies very, very quickly on a small region and slowly on another region. So in this small interval, the function varies a lot. And in this region, the function almost not varies. Okay? So typically, this is the stiffness of a differential equation. Here you can see it because they are huge parameters. So in some regions, the function will vary very fast, and in others, it will vary quite slowly. It's a difficult property. Change of state. Okay, yeah, this is the when event. When event. It's super useful, especially if you're an engineer and you maybe work on control or something like that, automatic control. the idea is you want to specify a change in the state that occurs at some time. Here I have the free fall of an object. So the object falls under the gravity. The differential equation is the Newton's second law. And I'm going to say here something new. I say that when the position of my mass is 0, that means that when the mass touches the ground, then the speed of the mass changes its sign. So when my mass is falling, the speed is a vector pointing to the ground. When it touches the ground, the vector is changed to the opposite direction, and it has the value the same as the speed when it touches the ground, but with a little coefficient r, which is a damping of energy. Okay? The energy is lost a little bit. And the oh, there's a lot of difference. A lot of difference. The main difference, if you want, is that this is compatible with the DSolve function. That's the simple answer. The more complicated answer is that if you want to use an if or something complicated, it should be specified inside a when event. Maybe here, for example, instead of this, we can have. I will show you an example. If x squared plus 1 is equal to that, then it should be specified here. Okay? And this when event has a lot of different options. For example, this is one of my favorite problems. If you want to reach a target, okay? I don't know, let's say you are here and you have some target which is moving and you want to catch that target, okay? So you want to send a catcher to intersect the moving point. And you have to solve the differential equation up to a statement when you don't know when it arrives. Okay, so you have to solve the equation while some condition is true. Okay, and that can be also specified as when event. Okay, it's the option stop integration. So here you have the solution. So this is the position of the mass over time. Here is 1, then it follows, touches the ground, it goes back, but with less energy at each time. Okay. Here you have the documentation of events and discontinuities. In the help page of when event, you have very nice examples too. For example, events, actions. This one is nice. If you are doing control, for example, you say that if I reach some value here too, then change the strategy. If you arrive to a lower value here, change strategy. For example, in finance, this can be useful. You know, if the value of the Bitcoin goes to that sell, if it goes to that value, then a buy. Something like that. But look at this documentation. There's a lot of nice properties. For example, bouncing balls. Okay, it's the same example. Crossing detection. Okay. Okay. Any other question? Yes. Yes.
The function to access to that information is so. Well, there are actually two. Is so and rip. I think it's maybe specified in one of the notebooks of the lesson today. Maybe the second one, actually, where we are working now. Let me check. No, I remember. It is in the documentation of when event. It is in the documentation of when event. So maybe here. Okay. Ta-da-da. There. Okay. So here you say when event print. Oh, I don't know. Sorry, I lost it again. Control A. Cell grouping, open also groups. Okay. So it is here. You have print. You select the condition to print. You have before t, so that's just a text. Then you get the value of t, okay, and the value of x of t and the value of the derivative of x. Okay, and you can do something like this. It was this kind of applications you were thinking about.
I need one.
Okay. So you want to see the steps of the algorithm, right? Like a step-by-step solution. Yes, the data of the solution, you can have it. Yes? 5 minutes, thank you. Yeah, just to finish, the answer to that question is when you get an interpolating function as a solution of the differential equation, it is an object, it's a box, but this box actually contains a lot of information inside. It is hidden. You have to open it to see it. For example, well, here there's no example, but the answer is yes. You have to write some lines of code, extra lines, but yes, you can access to a lot of that information. Okay. Any other question maybe before finishing this section? Okay, so if you want, you can take a break before starting the next one. We are going to talk about machine learning. Okay. Okay, 15 minutes. Yes, but it's not implemented by default by modules, so it means that maybe use some library that has it depends if your problem is like very complex problem. What do you have in mind?
Ça va? 2 petites secondes. Plus tard. See you later.